Hi and welcome to the very first Matter Over Mind podcast, or MOM as we've never called it before. I'm Stephen Mather and I'm a business psychologist with a bachelor's in psychology and a master's in organizational psychology from the University of London.
And I'm Thomas, an experimental physicist at the University of Oxford with a master's degree in theoretical physics, and I'm currently working on my PhD in atomic and laser physics.
Fantastic. And in a moment, we're going to get to our first ever topic. This is our first episode. And the question really is going to be around, can anything travel faster than light? Based upon a video that I have watched recently by the very well-known YouTuber Sabina Hossenfelder. But before we get onto that, because this is our very first episode, I thought it'd be useful just to kind of pad out a little bit what the podcast is about, and I suppose who we are and why we're kind of doing this thing. So how do you see it? What do you think the podcast is about, Thomas?
Well, like you sort of said, you sort of watched this video and they sort of throw around these terms, and generally a lot of science communicators, they're fairly good generally at sort of explaining the stuff that they're talking about. But I think sometimes it's lost in communication, the level of detail, or sort of rather the level of understanding required to sort of talk about the things in the way they do. So they might throw out some, complicated words or sort of describe complex systems like, black holes and that kind of thing, without really expressing, actually, there's a lot in the background that you need to know before you can really use those words properly. So sort of just explaining a little bit and giving more context to some of these more pop sciencey terms that are in reality quite advanced topics.
Yeah, and for me, from the physics perspective, I'm a very enthusiastic know nothing really. So I'm fascinated by science and physics in particular. So I listen to loads of these podcasts and I love them, So I love all these communicators. I literally have an earbud in my ear all the time, and I'm listening to these things, but they kind of will often throw in things like, for instance, the Lagrangian, and this is the Lagrangian. And then they just go on and talk about something else. And I'm thinking, that sounds like a character from The Matrix. What is that, So now I know I could obviously go and look it up, and that's perhaps what I should do, really. But they come thick and fast, and so in a way, it would be nice if this podcast could be a bit of a companion to those sorts of podcasts, or at least to you if you're somebody like me who likes to listen to this stuff. So there's the physics podcast in particular, and that's your area of expertise because you're an experimental physicist.
Yes.
And then the other side that we thought would be quite interesting to talk about is the bit that is my area of specialization, which is psychology. So what do you know about psychology, Thomas?
To be honest, not all that much. I mean, it's one of those things where every now and again I'll say to Celine, my fiance, or your daughter, I'll be like, oh, I wonder why people think like that, or we'll be kind of moaning about something that we hear in the news. I'm like, oh, why is that the case? And she's like, oh, well, ask Stephen, ask Dad. So yeah, basically every now and again I'm confused by how people behave. And me being a physicist, not necessarily too clued in on how people work. So it's good to have someone who knows about this stuff.
Cool. Okay, so you've given away the extra bit of nugget that I guess is part of our podcast, makes it a bit different, is that you're about to marry my daughter.
Yes, very soon now, in a few months actually.
That's right. And so you and Celine have been going out with each other for many years now. You sort of school sweethearts, if you like. And so we've seen you grow up, and I've watched you as you've learned more and more. You found your calling, which is in maths and physics, and so I then took advantage of that, because every time I see you, I've got questions to ask, and of course, every time you see me, you see it as an opportunity to talk about what you're doing, which I love. I think that's fantastic. I'm not sure how much our respective partners enjoy it, but
yeah, it's one of those things. I'll be talking away about physics every day, and then eventually there's a sort of a saturation point, a breaking point, where it's like, well, that's enough now. Let's stop.
Yeah.
And I probably hit that limit every day. more or less. So yeah.
Yeah. So as soon as we get together, we kind of sit in the corner and just start talking physics. And I do my best to keep up. But obviously, as you've got more and more knowledge, my pop physics knowledge only takes me so far. So it's become more and more challenging for me to understand what you're talking about. But I think this is a good opportunity for me to learn more personally. Also, for our listeners to listen into some of those conversations, and I'll also be able to say, from time to time, just a minute, what do you mean by that? And we can kind of get into that. So that's from my perspective, and then as you said, we're going to switch it every other week. So we'll also cover a psychology topic, and psychology has its own sort of, I suppose, social media infrastructure or ecosystem, let's call it. One of the most famous thought leaders, shall we call him, Jordan Peterson. He talks about psychology all the time, and he's got some interesting ideas. I'm not saying I agree with all of his ideas, but he talks about a lot of these things around things like archetypes and so on. And there's a lot of evolutionary psychology in there as well. And so I think that would be quite interesting to talk about, because lots of these influencers are talking the language of psychology actually and sociology. So I'd like to get into that conversation as well. So that's it. I suppose that's the as quick as we could, a bit of an overview of what we're trying to do with this podcast. And so yeah, I hope as listeners you find it interesting. If you've got topics that you would like us to talk about as listeners, please let us know, because obviously we'll pick those up. So if you watch a video about X or Y and you think I don't understand that, get in touch and we can do our best, particularly if it's around physics or psychology. If it's something else, then by all means throw it in there. We might even get a guest on from time to time who's an expert. Anyway, so yeah, please get in touch. All right, so we'll go back to our topic for today,
Hmm.
which is this idea around the speed of light. I was watching a YouTube video, as I said, from Sabina. She's talking about the speed of light, and she kind of, her heading for the video was something around, is it possible, or it might be possible, to travel faster than light? And then I started to look for other videos and so on. There's quite a lot of a discussion around this. So I thought that's a good topic for us to talk about. So I'll ask you that question really, what do we mean when we talk about the speed of light? What does that actually mean? And perhaps B, what do you think? Could it ever be possible to travel faster than that? Over to you, Thomas.
Okay, so I mean, the short answer, no. In my humble opinion, no. I don't think we'll ever travel faster than light. And there's a bunch of very good reasons why. So in the video, sort of it's addressed, some possible workarounds, which we'll get to.
Yeah.
But as a general rule, if you have mass, if you weigh something, no, it's impossible. And again, I'll sort of get to that in a little bit.
Yeah.
But before we start talking about, the can we travel faster than it, we should maybe know what light even is, right?
That would be my first question. Yeah. Tell me,
Yes,
what
yeah.
is light?
Yeah, so light in the very basic description, it's this intersection of an oscillating magnetic and electric field.
Whoa, I'm going to say whoa right now from the very start. Okay, so what does that mean?
So rewind the clocks back a little bit.
Yeah.
Historically, I don't know how long, but several hundred years ago, they sort of, you have particular mediums in which stuff travels through, and they thought light had to propagate through a medium to exist.
Was this the ether?
Exactly, yeah, the ether.
Yeah.
They figured it was this fluid-like substance that allows this light, whatever it may be, to travel through it. That's of course before we understood electromagnetism as we do now. But essentially, so you've probably heard just in the world that your brains have magnetic fields around them, right? Or they have a associated magnetic field. And also brains have electrical currents in them, right? So essentially, the currents in the brain produce the magnetic fields, basically.
Okay.
So there's sort of this interplay with if you have a moving charge, so an electrical current is a bunch of electrons flowing from, negative to positive.
Okay.
Um, when you have a flowing charge, it generates a magnetic field. Um,
Okay. So if I
on
was to say, okay, we've got a wire here,
mhm. Yep,
and A is the start of the wire, B is the end of the wire,
yep,
and we were to pass an electric charge through that,
yep.
that would be electrons bumping up against each other going through that cable, that wire,
hmm
and by doing that, it forms what you're calling an electric field around it. Is that right?
Yeah, so basically, there's this rule called the right hand rule, which basically, if you have a charge, you can sort of, if you point your thumb upwards and close your fist,
Okay.
the direction of your thumb, imagine
Yeah.
that's the current flowing from A to B.
Yeah.
The sort of direction of your fingers wrapping around your thumb,
Yeah.
that's where the magnetic field is. So basically,
Okay.
you've got an arrow, and then sort of almost spiraled around the arrow, you have your magnetic field.
So I think a lot of us at school. So I'm going back to my school days now. I did O level physics. That's as far as I got.
hmm
So for those of you not in the UK, an O level is gone. Well, not just in the UK, they're gone altogether now. But there used to be the sort of high school exam level that you do up to 16. Um, so that's kind of when I stopped doing physics as a subject. But I remember the iron filings and the bar magnet. That was
Mm.
kind of the way that we would visually see the. Is that a magnetic field? So you've got a bar
Yes.
magnet,
Yeah.
and you place it on the desk, and then you put iron filings around it, and you
hmm
can see the shape of the field around the two poles of the magnet. Yeah.
Yeah. So essentially, yeah, if you've got, every magnet has a north and south pole. It's always a dipole system, a two-pole system. So you've got north and south pole, and then yeah,
Yeah.
you imagine you draw a line from the top of the north pole round back
Mm.
into the south pole. So
Yeah.
you've always got north pole has arrows exiting, and south pole has arrows incoming.
Ah, okay. Right.
And the lines that those form, those are the magnetic field lines.
Got you. Okay. All right.
So yeah, sorry, yeah.
Yeah, good. Okay, that's great. So I've kind of taken you off a little bit of a tangent there, so
hmm
apologies. So let's get back to where you're up to now.
hmm
You would tell us where we go next.
Yeah, so as I said before, if you've got electrons traveling through your wire, you have charges traveling through your wire, they generate
Yeah,
a magnetic field, right?
yeah,
Well, similarly, in reverse, that also happens. If you have a change, so throw a bit of sort of terminology in here. Um, as the electrons are flowing through the wire, the charge is moving through space. So
okay,
you're having your electric field is changing. There's a change in the electric field. Obviously,
okay,
if you have electron in position A moving to position B, well, as it moves, position A now has less charge there, and now
right,
position
makes
B
sense.
has more charge. So the field is changing across your space. So the
Got you,
change in field is what generates the magnetic field.
got you.
So similarly, if I have a magnetic field, i.e., a bar magnet, if I wobble that around, um, the as the field lines sort of pass through a stationary charge, or it doesn't have to be stationary, but for this argument, a stationary
Mm,
charge, then the charge will start moving. So if I have a wire and it's not connected to a battery, and I have
yeah,
a magnet and start wobbling the magnet around, electricity will start to flow.
okay,
So basically, that is to say, a change in electric field generates a magnetic field. Similarly, a change in magnetic field generates an electric field.
okay.
So you could probably think to yourself, okay, well, what happens now though if I have a change in electric field, I have some current flowing, well, that's going to generate a magnetic field. That magnetic field is then going to influence the charge. So
Mm,
now there's going to be a change in magnetic field,
mm,
and that change in magnetic field will then change the electric field and so on and so forth. So you have
yeah,
this sort of one changes the other, therefore the other
mm.
one changes back and
Sort of
forth.
feedback. Mm,
Exactly. And then eventually you have two oscillating fields sort of complementing each other,
mm.
and then the sort of intersection of those two is light. Um,
Oh, wow,
yeah, just by
wow,
definition, that's what that's what light is.
wow. Okay, so I didn't expect you to get to that as quick as that. So, um, I'm trying to just think about what that means. Okay, so it's part of the magnetic. It's like a magnetic field. Then it's part of that electromagnetic.
Yeah, so generally, so what you use to describe that kind of material, if you will,
Mm,
is the electromagnetic radiation or electromagnetic
yeah,
spectrum. So
yeah,
light, the visible spectrum, is a few hundred wavelengths
yeah.
of frequencies of this band, but also that goes all the way from sort of radio waves, which are low frequency uh, waves, radio. Then you've got infrared. Then you've got visible light. Sorry, microwaves are in there. Visible light. Then you've got ultraviolet, um, X-ray and gamma and so on and so on.
Yeah. Okay.
I may have got some of the order wrong, but basically, yeah, you go all the
Mm,
way from radio waves all the way up to gamma rays, everything in between.
yeah.
That is just light or electromagnetic radiation. And what we call
Okay.
light is a very small snippet of that entire
Okay.
spectrum.
And I guess that's we are particularly interested in that because that's what our eyes pick up.
Mm.
So we have senses that allow us um, to to see things that are within that spectrum. So,
Yeah.
other than that, though, is there anything special about that frequency, or is it just that we can see that particular band or that
So
range?
in terms of that subset of frequencies, there's nothing inherently special about that.
Mm,
However, the interesting property of light is unlike charges or masses or anything. Nothing really can change the direction of light in the way that you may think. So you've got a magnet on the table. If I put a magnet underneath the table, I can move around the top magnet, right?
yeah.
Um, and basically, if you sort of zoom in enough on material, that there are atoms, right? So you
Mm,
have a bunch of these electric charges sort of buzzing around, interacting and engaging with each other. Light kind of doesn't really care about that. Light can just stream through. So it's pretty useful when you're looking at stuff because it means if you can see something, that's pretty much how it is.
mm,
There won't be any fields in between interfering, at least not on the scale that we exist at.
okay.
So it's pretty useful in that property. But the specific visible light spectrum that we see, there's nothing inherently special about that other than we just
Okay.
evolved to be able to see
Yeah. Yeah.
those
Yeah.
frequencies.
Okay. So we're thinking about the speed of light. So if
Mm.
that's light, so where do we need to go next?
So okay, so this is where we sort of leave the realm of electromagnetism,
Okay.
and sort of jump into sort of the realm of gravity and relativity,
Okay.
which might seem surprising, but
Yeah.
that's how it is. Um,
I am surprised, but carry on.
so as I said before, light travels in its direction and nothing really perturbs its path. Electric charges and so on don't really interact with it.
Okay.
Nothing really interacts with light. It obviously reflects and is absorbed
Mm,
by stuff, but nothing can twist its direction. Light travels in a straight line. So you're probably thinking to yourself, well, that sounds like a load of rubbish because gravitational lensing that
yes,
exists. What's going on
and
there?
also, like if you put a pencil in water,
Hmm.
then it looks like the pencil's bent. So that suggests
Yes.
that it is bending there as well.
Yeah. So when you put it in like the water or something, what's happening there essentially is different materials. They have this thing called refractive index, like travel in a straight line. And then if you put a block of transparent plastic, obviously that optical density of the plastic is more than just the air around us. The light still travels in a straight line. It knocks off course. So
Diverts.
yeah. So you've got an arrow, you shoot it in a straight line.
Yeah,
Someone parries it with their shield. It's still going in a straight line.
got you.
It's not sort of spinning around. It's a
Just
straight
been
line.
redirected. Yeah,
Yeah, it kind of
and
bounces
it's
around.
still straight.
It's still straight. It just
Okay.
means yeah, if you put the pencil behind the thing, you can just see instead of front on in the pencil, you may see a little bit of the left or right of it,
Mm,
which you wouldn't ordinarily see. So it has this weird
mm,
warbly appearance to
mm.
it.
Okay.
So that was a good caveat. Light travels in a straight line,
Yeah.
but this effectively the speed of light does change depending on what material it's in. So
Okay.
when they say you can't travel faster than light, it specifically means faster than light in vacuum.
In a vacuum.
Yeah,
Yep.
so a
Okay.
vacuum basically means there's nothing there, there's nothing to sort of stretch or squash the light, so the
Yep.
light just travels, um, unperturbed. Whereas
Got you.
in air, there's a well characterized sort of optical density of air, and then the same with some plastics and so on.
Sure.
But yeah, so in vacuum, that's the one that you can't travel faster
Got
than.
you. Got you.
So there might be some eagle-eared listeners, if you will, saying, "Well, Cherenkov radiation exists,
Yeah.
so what's all that
Okay.
about?" No,
Yep.
that basically. So sometimes you see if you Google Cherenkov radiation, it's basically a glow that you get in some nuclear reactions, and that
Okay.
glow is because um, particles are traveling faster than light in that particular medium.
Okay.
So you get this. It's kind of like the sound barrier cone that you get
Yeah.
with supersonic
But that only
stuff.
happens if it's in a medium like air.
Yes, yeah,
Got
yeah.
you. Okay.
Well, it wouldn't be air; it would be some,
Oh, okay.
heavy liquid or something.
Okay. Got you.
Um, but yeah, so faster than light can't exist in a vacuum, I should say.
Okay.
But yeah, so okay, so you can deflect light by putting different densities materials in front of it. But now imagine we're in space. There is no
Yep.
material now. Light just travels in a straight line. So how is it that gravity bends it? I mean, this is a bit of a detour, but kind of, I guess, what is
Mm.
gravity, right? Gravity, it turns out, also is a field, or rather is described by a field in a similar way to electric fields or magnetic fields and so on. It's also, you can imagine it as this surface with sort of hills and troughs and so on.
Mm. Mm-hmm.
And it turns out in the field of gravity, um, everything kind of has to follow set trajectories, or they're called world lines, maybe you might
Okay.
hear them called. Um, and essentially, imagine you've got basically the fabric of reality. You have your three spatial dimensions for us, three-dimensional beings, and you have a
Yep.
time. So obviously, time always moves forward.
Mm-hmm.
Um, so now imagine you have this sort of four-dimensional geometry, and there's infinite number of paths on this geometry. Stuff can only travel along these railroads, um, and in a flat space, which is basically normally what we exist in, or on our small person scale,
Mm-hmm.
everything's flat. And again, at some point, I can explain what that might mean.
Yep.
But basically, light travels along these paths in this, in this space-time geometry.
Yep.
Um, Turns out gravity bends this geometry,
Yep.
so which means what are straight lines to light in this geometry, because they're traveling along these tracks, all these
Mm.
world lines, gravity bends these lines, so light can get bent that way. That's the
Mm.
only known way to bend light in vacuum. It's by a
Got you.
gravitational field. So that's what
Okay.
gravitational lensing is.
Okay.
Um, yeah.
Okay. So let's just take stock there. So um, this is the effect. So when I've listened to podcasts about astronomy and things like that,
Hmm.
they talk about gravitational lensing, which allows us to kind of look behind stellar bodies that we wouldn't be able to see otherwise.
Hmm.
And this is because the thing that's behind the thing that's blocking it is a big mass, big body.
Yeah.
And it's because it's got such a lot of gravity,
Hmm.
it's literally creating a gravity well or a gravity, well, a bend in the fabric of space time. Is that what you're
Hmm.
saying?
Yep.
And so if you were to shine a light to that, it would like it would if you put a bowling ball on a trampoline, it affects the way that something would go round it. If you were to throw a marble on it, it would go round it because it would be
Yeah.
sort of affected by that huge great body. Am I right in saying that this was predicted by the maths before we actually saw it, or did we see it and then explain it?
Um, to be honest, it's kind of tricky, that one. Like,
Mm.
there's a lot of things in physics which is kind of like the chicken and the egg sort of argument,
Okay.
where it could be. I mean, even the equations for gravity, to derive them,
Mm.
there's the method that you kind of learn, which I won't bore you with how to do that. And then the the kind of starting point to derive the equations has another person's name in it, not Einstein. It's the
Yeah, yeah.
Einstein-Hilbert action you use.
Okay.
But obviously, the
Yeah.
Einstein's field equations, which describe gravity. So it's kind of, well, who did it first, Hilbert or Einstein, right?
Yeah.
Um,
Right.
Hilbert also comes up in quantum mechanics a lot, but
I've heard of Hilbert space, but let's not get into that.
yeah, let's not
But I've
get
heard of that.
sidetracked. But yeah, so to answer your question, I don't really know actually
Okay.
whether they saw lensing first and tried to explain it, or Einstein came up with his clever way of describing space-time and then thought, oh, interesting,
We should be able to see that.
we should be able
Mm,
to see that.
mm,
And it kind of, like I say it makes sense if you look at the equations.
mm.
To somebody who's done general relativity, it kind of is obvious if you look at the
Yeah.
equations and know what they mean. But basically, the reason is, like I say, imagine, yeah, because of how mathematically you describe space-time, or just what we
Mm,
exist in, it is effectively like a set of grid points that are infinitesimally close together. And yeah, we as people can kind of travel wherever we want, but yeah, light always moves in straight lines. So if you fold the racetrack, if you will, well then the
mm.
cars have to now start turning to stay on the
Got
racetrack.
you.
You
Yeah.
can't leave these world lines. You're all
Yeah.
kind of fixed to them.
Yeah.
Um,
So they follow the geometry, the space time geometry,
mhm,
which we can probably get into that another time, to talk about what that means. But
mhm.
I think most of us, if we're interested in science, we've seen those pictures and illustrations and videos of a sheet that is pulled tightly
Yeah,
and heavy balls on there that show you kind of visual representation of the fact that heavy bodies distort or affect the sheet, which for us is this space-time geometry. So
yeah.
I think most of us kind of can get that. Okay, that's great. Where do we need to go next then? So I think we're on our way.
Yeah, so that's sort of, I guess, getting some caveats out of the way.
Yeah.
But we still haven't answered the question of yeah, can we travel faster than light? Um, so so as I mentioned before, that light travels on these world lines. So to sort of use a slightly different picture, so imagine you've got a cone, which if you Google anything to do with space-time, you probably will come across space-time cones,
Yeah.
which looking at them with no more context other than the Wikipedia page will tell you nothing.
Okay.
um, so essentially, imagine you've got a cone. The cone kind of represents three areas of space you can exist in. Along the surface of the cone, that's effectively light speed. So imagine you've got your y-axis is time, and your x-axis is space, and draw a 45-degree angle from that. So if you're traveling at the speed of light, you're effectively setting that boundary of, as 1 second travels forward, you travel x distance, a fixed distance, right?
Okay.
So that's sort of your, so anything on the surface of the cone basically is what's called, has a null-like trajectory, that they may call it, and basically that just means it's a trajectory which um, time and space are essentially fixed. They're constant, and basically what that means is you're traveling at the speed of light. So
Okay.
in special relativity, or even general, if you expand a little bit, anything that has effectively a null action, or a zero trajectory, basically just means it's traveling at light speed, or also it has no mass. I understand it's a little bit confusing, but just take my word for it. You have a cone, anything traveling on the surface of the cone has to be at the speed of light.
Okay.
If
So let me just try and understand this. So I'm imagining a cone, like an
mhm,
ice cream cone.
Yep.
Okay. And the cone, the pointy bit is what at the top?
The pointy bit's at the bottom, and that's at time zero. That's at the
Okay,
start.
so the pointy bit is at the bottom, and we're saying that that's where time starts.
Yeah.
Okay, and then as we go forward in time, we're going up the cone.
Yeah. Yeah. Yeah.
Correct.
Yep.
So as though we'd put a stick or a pencil in the middle of the cone, and we're saying that as you go up that pencil, you're traveling through time. Is that right?
Yeah. Exactly. Yeah.
Okay.
Yeah. If you, and the other directions basically, inside the envelope of the cone, if you will, inside the hollow bit of the cone,
Yeah.
that's space. So
Okay.
if you can stay still and not move anywhere in space, in
Yeah.
which case you're just going to move up the length of the cone. You're not
Got
going to
you.
move around in the cone. You're just going
Yeah.
to stay in the middle. If you decide to walk about, then you're moving in time, also space. So you walking around
Yeah.
is you're moving in space, and moving in time just kind of happens in the
So
background,
so
basically.
imagine you've gone into miniature, and you are now living inside of this ice cream cone. Um, you cannot help yourself moving up the cone, so you will always be moving up the cone.
Yeah,
But you can move around to the left or the right, east, west, or whatever,
yeah, yeah.
um, and you can do that at the same time as going up.
Yeah,
Yeah.
exactly. So going up, maybe the cone upside down might be a better analogy. You're falling. You're always falling. You can't stop falling. So you're
Okay.
traveling through time. You're falling through time. But I don't know. Say you've got a I don't know, parachute, and you can pull it left or right. So you can kind of move around the cone.
Okay.
But you're always falling down. You're always
Okay.
progressing in
All
time,
right.
whether you like it
So
or not.
let's turn the cone upside down then, and we this is a huge, great cone, like an ice cream cone, and you're stood at the top of this cone. This is the beginning of time.
Hmm.
You jump inside. There's a little hole at the top. You jump inside the cone, and at that point, you're falling down, and that's you're likening that to traveling through time,
Yeah,
which we all do. We can't help ourselves. We are always traveling forwards at 1 minute per minute
yeah,
through time. But of course, we can move in space. So if we're on this parachute, we can move to the left or the right, and that's kind of us moving from one place to another.
yeah.
And okay, got you.
Yeah, cool.
Yeah.
Okay, so I've sort of in my head I've figured out how I'm going to sort of
Okay.
drive this point home. So suppose you're looking at the edge of like so the walls of the cone as you're falling down. You're moving around in space, and you're like, you know what? I'm
Yeah.
going to touch the wall.
Yeah.
I want to get to the edge of this, the sort of the wall of this cone, the inner wall. So you
Mm,
pull hard on one of your directions of your parachute, and you're
yeah.
zooming towards the cone wall. But you notice, obviously, because it's a cone shape, the farther down you fall, the wider the cone is getting. So,
Yeah.
you pull hard on the thing and you feel like you're getting close to the wall, but the wall's just getting farther and farther away. So you pull even harder, you try your absolute best, but there's no matter how hard you pull, because you're always falling down, the
Yeah.
wall gets farther and farther because the cone gets wider and wider
Yeah.
as you sort of get towards the base. Well, it's infinitely far away base, I should say.
Yeah.
So and but then you see this cheeky little chap skating on the surface of the wall,
Okay.
and you're well, how's he doing that? How is this person
Yeah.
on the surface? Well, unfortunately, you got the parachute on, which is analogous to mass in this case.
Right.
Because you
Okay.
have mass, you're too slow to reach the wall. You're falling, and you can't quite get enough. Yeah, but this character skating on the surface, he's not.
Yeah.
They've got no parachute. They can, they're
Yeah.
sort of they're nice and
Mm,
breezy, and they have no parachute. They have nothing slowing them down essentially.
yeah.
So they're happy.
Yeah.
They're traveling on the surface, so that's having no mass. So they're effectively a light speed particle.
Wow, that's on the inside of the cone. They're skating on this inside of the cone, and that's analogous to not having any mass.
Yeah, essentially. So basically, the only
Yeah,
way you can you can leave the inside of the cone to touch the wall is if you're fast enough. Basically, if you can catch
yeah,
up to the
yeah,
speed at which the wall is traveling away. And that speed
yeah.
happens to be the speed of light. So unless you're traveling at light speed, you can't touch this wall. You can't have a null-like trajectory, as the terminology might say. Um,
Okay,
so you're probably thinking, okay, well, cool. Well, what's outside this wall then? Okay, so if you're on the wall, you're at light speed. Well,
yeah,
maybe if I break out of this cone, then maybe I have more. Maybe the character skating on the wall, they find some kind of a propeller, and then they shoot themselves out.
yeah.
What would that look
Mm,
like? So there's actually a name for stuff that exists outside the cone.
okay.
The term's called tachyonic particles or tachyon particles,
Tachyons.
or
I hear about those on Star Trek a lot.
yes. So now the now I'm no particle physicist, but so
Okay,
maybe someone would disagree with me. But this
okay,
is my interpretation of what tachyons are.
okay.
So anything on the inside of the cone is a massive particle, a particle with mass, or a particle that travels in space-like trajectories or
Hmm.
on space-like trajectories. So that's got a name. Then the second part of the diagram is the line or the surface of the cone. So those are, you know, massless particles or light speed
Hmm.
particles, or particles that have null-like trajectories.
Yeah.
Well, there's another third of the diagram that no one's talking about, so that also has to have a name. So whoever
Hmm.
it was decided, cool, let's just call that stuff tachyonic particles, particles with
Right.
space-like trajectories. So it's just a classification because you've got two-thirds of the diagram labeled, or what's
Yeah.
the stuff on the outside? Well,
Right.
let's call it a tachyon. So it's like I say, there maybe is some particle theory somewhere that explains actually they have some real properties, but for the sake of argument for relativity and how I understand it, they're not really anything. It's just a label because someone was like, well,
Yeah.
what we call them
We need
that bit
to
then.
we need to call that something. All
Yeah,
right. Okay.
yeah.
So let me just make sure I understand it. So going labeling this diagram, then we've got the bit inside the cone, the area inside the cone.
Mm-hmm.
Um, that's um, that's time essentially,
Mm-hmm.
or that's going through time,
Yep.
and then moving left and right, and that's moving through space. And then you've got people that are, or the side of the cone, let's say
Mm-hmm.
anybody that happens to be able to be on the side of the cone on the inside, they're massless.
Yep.
And then we've got this other question of what's outside. If you were to drill a hole in the cone
Mm-hmm.
and get outside it, that would be where your tachyons would live, if there were such things, and we don't have any evidence that there are.
Mm-hmm.
But it's just what's outside.
Yeah, essentially. So that's not really answer the question of why you can't, but that's sort of the
Yeah.
picture as it is at the moment. If
Okay.
you if you're on time-like trajectories, basically that just means you're on trajectories dictated by time. You can move around any way you want, but time is always moving for you. You don't have control
Yeah.
over that. If you're
Yeah.
on the surface, you're effectively fixed in this weird kind of limbo space where
Mm.
time and space kind of don't really change for you. I mean, this is sort of a bit hand wavy, but essentially
Okay.
that's what the equations seem to tell you. Your time is
Okay.
fixed, your space is fixed, everything is just kind of a bit constant.
Okay.
And then anything outside your space-like trajectories, because now the only thing dictating what you're doing is your space, your time. You can kind of do what you want with that.
Right.
Of course, like I said, they don't really exist, but that's the sort of the picture, and
Okay.
that's maybe why they call it space-like, time-like, and null-like.
Okay. So the reason, so from what I've got from you so far, and this might actually be the answer to the question, maybe we sort of wrap it up, but it sounds like what you're saying is that the way that the geometry of space time is that as you're traveling down this cone, you're traveling at whatever, the normal time, the speed at which it goes.
Mhm.
You can't ever get to the wall, because as you are moving through that time, as fast as you can move across, because of the nature of a cone, it's getting bigger all the time. It just keeps going away from you constantly, so you never can make it. And
Yeah.
that's the kind of way to think about it.
I mean, yeah, essentially, yeah. That's, I mean, yeah, that's the sort of, I guess, the sort of heuristic, hand
Yeah.
wavy
Yeah.
description. It doesn't really answer the why, but it's more just this is kind of how things work.
Is there any more why?
There's a little bit more why. So,
Mm.
um, essentially, this may get a little bit more abstract, but so I should probably rewind a little bit. So at the start of the
Mm.
video, you mentioned this video that you watched,
Mm.
Sabine Hossenfelder, and she kind of argues in that video that actually, on a technicality, you can, in principle, or rather, there's nothing saying you can't travel faster than light if you have no mass.
Yeah.
Um, I little bit disagree, but the maths is such that you can kind of do this acrobatics with it, such that
Mm.
it's technically not saying no, or at least with our current theories.
Okay.
Um, and you can do this by basically messing around with reference frames. Um, so, so imagine you're on a train, and the
Hmm.
train is traveling at 100 miles per hour,
Yeah.
and somebody else is standing on the, on a bridge or whatever, watching the train go by.
mm,
And now imagine this train is made of glass or something, is fully see-through.
mm,
So the person on the train, if they start walking forwards,
mm,
then the person on the bridge watching the train go by is going to see that person traveling at the speed of the train, 100
mm,
miles per hour, plus, say, the 2 miles per hour they're walking. So they're going to
yeah,
see that person traveling 102 miles per hour. The
mm,
person on the train is only walking at 2 miles per hour, so
mm,
they see themselves only moving relatively slowly.
mm,
Um, so that's, so generally speaking, if you're on a moving object and you move yourself or throw something in the direction of travel, the speed of that thing is going to be the two speeds added together, basically.
yeah, got
So
you.
that's
Yeah.
the very basic principle of special relativity. You have this effect.
Mm,
Um, so you're probably thinking, okay, well, if I'm on this train and I shoot a laser pen forward, well, then
mm.
the laser light is going to be traveling whatever speed the laser would travel at, the speed of light, plus the speed of the train. Well, it turns
Plus
out, no,
100
that's
miles
not
an
the
hour.
case. That
Yeah,
doesn't
yeah.
actually happen. It's
Mm,
always at the speed of light.
mm,
Um, so using pure special relativity, and this is the case where everything is either moving at a constant speed or is fully stationary. There's no acceleration, meaning there's no gravity.
okay.
Um, in special relativity, there is no way anything can travel faster than light, simply because imagine if someone is outside of the cone.
Yeah.
They can kind of move around wherever they want. So if I drop drop a ball on the floor, so everyone inside and even on the surface of the cone is going to see that ball fall and it's going to hit, right? If you're outside the cone, because of the way the space works and because of the way the maths works, you may be able to position yourself in such a way that you actually see the ball touch the floor before you even see it being dropped. So as a result, there's a sort of a causality issue. You're seeing
Mm,
something, you're seeing the result of something before it's happened. So
mm,
using pure special relativity, you kind of get these strange paradoxes if you try
mm,
and go faster than light. Um, it's kind of confusing to, especially in a audio format,
mm.
illustrate what this means. But in the
Yeah.
video, in Sabine's video, there's a nice little cartoon to kind of explain what
Mm,
I'm talking about.
yeah.
Um, However, when you now start introducing accelerating reference frames, so you move into general relativity, then you can do some more wacky stuff where you can kind of the same rules don't quite apply.
Mm,
So you can kind of massage the equations and the geometry such that actually you can kind of get around that sort of time paradox troubles. Um, and it's kind of there's no real easy way of explaining this
mm.
without going into a
Sure.
substantial amount of detail. But essentially, using special relativity, no, it is fully and wholly impossible. Using general relativity, you can kind of argue a particular way, but the caveat there is if you have mass, you still cannot reach the speed of light, regardless of what theory you're using to describe,
Mm,
and that's because essentially to accelerate or to move, to gain speed, you need some energy.
mm,
And effectively, there's a scaling term, which means the closer you are to the speed of light, the closer to zero this thing becomes. And it turns out, if you look at the maths, you've got energy is equal to your rest energy divided by this term. So if you divide anything by a small number, it gets big, and the smaller that number is, the bigger the term gets. So if you imagine, let's say I have this number, I divide it by one, it's just the same number, it's itself. Anything
mm,
divided by one is itself. I divide it by half, well that then it becomes twice as big. I divide it by a quarter, it gets 4 times as big, and so on and so forth. The
mm,
smaller the denominator, the larger the number. As you approach the speed of light, the closer this value goes towards zero. So if you kind of follow the sort of argument, the closer you get to zero, the bigger the number, i.e., the bigger the energy,
mm,
um, until eventually you get to zero. Once you reach the speed of light, you're dividing by zero, and you get an undefined number. Effectively, your value jumps up to infinity as fast as you're approaching zero, and you kind of get this either infinite energy required or sort of undefined amount of energy required. So essentially, it's just this mathematical wall, basically
mm,
saying the closer you are, the more energy you need, and the closer you get, even more energy is needed, until eventually you get to the point where you either need zero mass to balance the zeros or infinite energy to counteract how quickly you go into zero. So it's a bit abstract and kind of hard without a bit more mathematical background, but essentially, yeah, that's what you need. You either need zero mass to cancel the zero, the sort of the denominator zero, or you need infinite energy to essentially get there faster than you get into zero. These two things kind of balance the equation and then allow you to travel at light. Obviously, we have mass. Anything really that is sort of physical has a mass associated with it, and as such, you will never break that barrier unless you have an infinite amount of energy. But then you run into this problem where, at a point, that energy is just going to be converted into more mass. So then I need more energy to accelerate this bigger thing, and again, it's just a feedback loop. You get this sort of asymptotic relationship where you can't ever reach the end.
Okay, I'm going to let that one go. That asymptotic relationship. Let's leave that for another day. Okay, right. I think we've gone longer than we planned to. So I think what we should do is we should bring this episode to an end. All right, but I've learned something there, and the whole explanation around the cone, as somebody that doesn't know the maths, and I do appreciate this is always the challenge for communicators when you're trying to explain things like physics that is so dependent upon the maths. It's like trying to explain something in a different language. It's sometimes very, very difficult. So I really appreciate that, and I think I've got a better understanding now. And that cone example is the one that I'll just keep coming back to. For me, that just makes sense in my mind. So that's good. Cool. Thank you very much, Thomas.
Yeah, I mean, thanks for listening. I got a little bit carried away a few times, but yeah, no, it's good to talk, and it's good that you sort of call me out on when I start getting a bit too technical, because I can very easily fall into just throwing out jargon because it's easier to do that.
It's just a complicated topic, isn't it? All right, so good. Next week or the next episode, we need to find a psychology based one. So we'll have a think about that. We won't announce that on this episode in case we change our minds. So we'll find that for next week. So next week it'll be kind of role reversal. So it'll be you asking the questions, and I'll be trying my best to answer it as best I can without using the psychobabble. So that's where you can call me out on that.
Yes. Yeah.
Okay, good. Well, thank you everybody for listening. Hope you enjoyed our very first episode. This is our first episode, so hopefully we'll get better at it. I feel like it went okay. But please, give us some feedback. Please, whatever you need to do on the podcast app that you're using. I mean, we're definitely on Apple Podcasts. Hopefully we're on Spotify and some of the others. They have different things you need to do to follow or subscribe or whatever. So please do that. We're hoping to get on YouTube as well, so follow and subscribe to that. Currently, we're an audio-only podcast. It's just a lot easier for me to edit it and all of that. But please contact us. We've actually got an email address, which is matterovermindpodcast@gmail.com. That's matterovermindpodcast@gmail.com. If you want to talk to us, give us some ideas for topics, or if you want to give us some feedback about what was useful, what wasn't, what you liked, what you didn't, then by all means do that too, and we'll either take it on board or completely ignore it. So by all means, please do that. Great. Thank you very much for listening, everybody. For now, bye. Say bye.
Bye.